Hi everyone, welcome again to the channel. I've got a really exciting interview for you all. I've been after this interview for a while, but it's my pleasure to invite Aart de Geus to the channel. Aart is the CEO of Synopsys, so thank you for joining us.
It's a pleasure to talk to you.
So yeah, 37 years of Synopsys. You as CEO.
Well, joined from kindergarten, right?
Yeah.
That's sort of the idea.
You still look 21, don't worry.
Oh, thank you. I'll behave like that.
So you've been in this industry for a while and you've had so many awards. I mean, Robert Noyce Award, GSA Awards. Major things that you've seen the industry change from CAD to EDA. What have been the highlights?
Well, in many ways, the highlights almost always start by accidental events that suddenly put you in the middle of some opportunity, right? And so, the story is longer. Mm-hmm. The whole synthesis thing started while I was working at General Electric.
Yep.
And GE decided to get out of semiconductors. We will all get laid off. And after a lot of different pathways, finally had the opportunity to essentially spin out the team or a piece of the team and the technology with GE support, so all above board things, and then introduce what was then still somewhat of a prototype to a market that was ripe for it, because people were designing groupings of 300-500 gates maximum.
Yep.
And here this thing could do it automatically and get better results. And so it's only when you look back many years later that you see that it happens to be, you actually mentioned the term, I think, a watershed between CAD, computer-aided design, and EDA, electronic design automation. And the automation was really one of the things that digital design needed. Because digital design, not then called Moore's Law, but was waiting for Moore's Law because it was primed for it. And of course, in order to do that, you have scaling and scaling and scaling. And an exponential is a wonderful curve, right? It's a self-multiplying one. And so we were on that curve and managed to stay on it. But being part of that moment, in the moment, just was like, whoa, we're doing stuff and we're moving fast. And in hindsight, you can see the implications. And an estimate would say that looking back today, we helped with about 10 million X in productivity.
Yeah, I was looking at
which adds up, right?
Yeah. What else has 10 million X in that time, right?
Well, in all fairness, around the mainstream of this automation from synthesis, then it had to be accompanied by the ability to automatically do place and route.
Yep.
And if you then have sort of the function and the form together, and those can work on an exponential basis, now you have something that really is going to move fast. And that became the massive differentiation between digital design and all other forms of semi-custom or custom. And, we've reaped the benefits. And actually, there's still more need for it.
Yep. Yeah, so when you were doing that, the spin out essentially from GE taking the team, did you think this was going to be a widely generalized productization of design, or was the thinking more kind of blinkered in that sense?
Well, it was so accidental, because at that time at General Electric we did gate arrays, which are essentially rows of transistors, and then you could put metallization on top, and that became then NAND, NOR gates, and inverters. And I had heard, or actually spoken to somebody who had pioneered this notion of BDD, binary decision diagram, which was just another word for multiplexers. And so I asked the designer friend at GE, hey, can you put some multiplexers on that array? And he did the metallization for that. And then we gave that to the designers, because presumably if you had multiplexers, you could design much more efficiently some of the functions, which turns out to be true. I'd not quite understood at the time that multiplexers are essentially transmission gates. So the signal, when you have multiple one of those in a row, is not that great. But the problem turned out to be that they couldn't design with it. They didn't know how to use them. And I thought, hey, why don't we just write a program to do that automatically?
Yep.
Just write a program, not having a clue that this thing was called synthesis. But that's essentially what we invented. And then later I discovered, of course, that there are other people that had done wonders already.
It's this industry was one of the first to coin the term kind of AI for the synthesis and the place and route, but it was still very much heuristic AI rather than machine learning as we're thinking about it today.
Well, our program was called Socrates, and I have to carefully remember what it stood for because it was synthesis and optimization of combinational circuits using a rule-based and technology-independent expert system. Socrates, easy to remember.
Yes, clearly.
But it was seminal. I just like to highlight rule-based expert system, right? And so now suddenly I'm a pro at AI in the early days. But I often forget to mention that you would add rules, it would get better. You add more rules, get better. You add more rules, it didn't work so well anymore because the conflict. And of course, it has gone through many evolutions. And now all the way fast forwarding to today, of course, AI is all over this, both in machine learning, but also in looking at entire design flows.
So going from the sort of the 100 gates, 1,000 gates way back then, and now we're dealing with billions, if not trillions of transistors. How have you seen chip design change in that time?
Well,
or the attitudes to chip design, I should say.
The attitude to chip design. The attitude hasn't changed one bit. Tomorrow is a lot harder than yesterday.
Sure.
And we're going to go for it.
Okay.
That has not changed. And I would say for a long period of time, the exponential, maybe not exactly the way Gordon had stated it, has essentially continued. And in a minute, I'm sure we'll talk about the fact that there's a whole new exponential on its way now. But there are some phases, because if I look at the circuits of then, and I happen to find a few in my drawer on paper, the first thing I realize is there were only two metrics. And the metrics at that point in time was the number of gates and the speed of the circuit. And the fact that it was just the number of gates, not even the layout, tells you something about how tightly these things were packed or not. And then, of course, it became, of course, area versus speed. And it's really towards the end of the 90s that power became more and more important. And then, of course, by the time early 2000, you now have essentially smartphones or any phone, as a matter of fact. There's this thing called battery life. And we barely remember, but when you could do a phone call for an hour, it was amazing. And now it's like, no, I want to, look at the internet for 5 hours in a row and play games and God knows what. That is an enormous change, but it is possible both through an incredible increase in speed, complexity, and power management, right? And I will fast forward right now and say for the next 20 years, power is going to be the single biggest issue at the most micro level, at the thermal level, and at the humankind climate level.
I often see chip companies, they go through a very cyclical nature of performance, then efficiency, then performance, and then we're going through another one of those efficiency scaling things right now.
Well, another way of describing it the same way is the first one in a series is performance, and then efficiency while you're working on the next generation, right? Because the generation's invariably driven by what gives you the most marketable differentiation. And not to belittle one bit the efficiency, because cost has always been key, but if fewer devices just better, because the rate of change is so high, it is what determines the leadership on Moore's Law. And the most challenging and at the same time most motivating thing has been, how do you for dear life hold on to that Moore's Law or whatever the equivalent is. And I use Moore's Law, this notion of exponential, as really the characteristic of 50 years of mankind, right? Be able to do that. There have been other Moore's Law before. And so in the 1500s, book printing, in 50 years arrived, I think, at about 20 million books. But those books change humanity, right? And then, of course, you can do that with the engine age, the industrialization age has similar characteristics. This one has sort of gone for a while. And the funky thing is, as the traditional Moore's Law is slowing down, not stopping, because it's amazing, the new technology is still coming out, there's meanwhile this whole different Moore's Law that says, I do want actually 1,000 times more transistors. And the way we're going to get that is we're going to put chips so close together you wouldn't believe it, right?
The worry is that we'll run out of power before we hit it.
Yeah, but the whole point is that we use these chips to do AI, and AI is going to resolve all the problems in the world.
The universal solution.
Yeah, exactly. And therein lies, of course, the fallacy, because that the computation needed is going to be enormous for this, and the hunger will be enormous for it, because it does bring differentiation in everything going forward. And already now, all the hyperscalers are trying as fast as possible to secure their own sources of energy. And in all fairness, they try to go green as much as possible. And so the net neutral push will be in our industry continuing at a feverish pace, because of course we are electrified, so that's already the common vocabulary of energy, right?
Yeah. So one of the recent trends is this chipletization, open chiplet marketplace, however you want to transition. I remember back in the late 80s and 90s, the very similar thing was being thought about, and then everybody went into monolithic, and now we're breaking out in chiplets again. How is this era of chiplets different to back then?
But I don't think we quite made it to monolithic, right? We never put power devices on that same chip. We didn't do analog mixed signal.
They're trying to.
No, the trying is always good. It's always good, right? But we didn't do memories on logic chips. But at the same time, now we find that the memories are full of logic. So which way did it go? And but you're pointing still in an interesting direction, which is the notion of being able to bring things that are heterogeneous, meaning different in the very technologies that it takes to make them successful, is a fantastic opportunity. And I like to call this next exponential age, SysMore, for systemic complexity, in contrast to the classic Moore's law, that scale complexity. And I know this scale complexity demands a lot of systemic understanding. I get that. But fundamentally, it was more transistors, more transistors, bring the cost down, glue them close together on one chip. Now we have multiple chips. So right there, you have a whole new set of dimensions to play with. You have the heterogeneous capabilities. And the single thing that is most relevant in making that transition possible is actually the unbelievable progress in the last 20 years of connectivity between chips. It's far from resolved. There's a lot of thermal this and that somewhere on the way, but the fact is nonetheless that there's been 100,000x improvement in pin density possibilities and so on, and so that opens doors. And of course, everything then questions architecture. I'm sure you'll get to that.
We're moving from this sort of 2D chiplet ecosystem, and now some companies are going 3D. Let's do chip on chip on chip, not only with memories but logic, and it's getting extremely complex. And I remember speaking to companies when they were first doing it, and they were saying the software tools need to catch up. How much of a change has it been for you guys dealing with vertical stacking rather than just simply horizontal chip?
I love it always when the users say, after we put an unbelievable push forward, 100x, they say, but the tools should be able to do more. And of course, on one hand, you think, hey, can you just acknowledge what we did yesterday for a minute? But at the same time, it's fantastic because we like sort of unhappy customers, because the really good ones are unhappy because they suddenly see the next opportunity, and then it's like the minute you see it, you're already late, right? And luckily enough, we saw this coming a number of years ago and started to invest in that. And you're right, this 2D, 2.5D, 3D, but it's all in the same ilk, really. It is, for starters, proximity and bandwidth, and then of course the speed of that, but also the energy between those. And then the minute you get truly layered on top of each other, you have manufacturing challenges, you also have testing challenges or repair challenges. And of course, the closer together, the more thermal is sort of your common enemy, right?
So how many of those features end up being meeting the customer at their demands versus things that you guys are inventing internally?
I think we are much more in the inventing internally than we were, let's say, in the late 90s.
Yep.
Actually, in the late 90s, they had sort of this four-letter word for us, which is, it wasn't four letters, but it was,
Okay.
When are you going to make up the design gap?
Yeah,
and it was always like, well, you're guilty that we cannot design just anything we want. And while there was some truth in terms of one could manufacture more things that one could necessarily design automatically, we have long caught up with that. And with relatively clear definitions of what you want to get, we can automate pretty much anything. Automating it well is not any different than making transistors well. And if you make them much smaller, they are harder to build, but it's cool to push, right? Same, it's cool for us to push.
So in this era of machine learning, I like to be very distinct when I say AI versus machine learning, because for me, machine learning is the next generation of compute. But we're starting to talk to companies now about applying machine learning in the tool for actual chip design. I think when we last spoke, that was kind of the big announcement of Synopsys' AI or machine learning tools to help in that sort of co-design. How has that changed how you're approaching?
So we spoke at the Hot Chips conference, I think.
A couple of years ago,
Yeah. And at that point in time, I think we were sort of more forthcoming about what we had in terms of being able to really have multiple tools that, for starters, worked very well together. And that's an important point.
Yep.
And out of that, be able to take a piece of design flow and automate it completely. And by the way, because we could do that and have multiple perspectives on the design, actually simultaneously get better results. And so this took typically a few months of work and turned it into a few weeks of work. And that was remarkable. But aside of that, it had exactly the same characteristic as the synthesis of whatever 30 years earlier.
Okay.
Because there too, what happened then, and I'll explain this one, which is what happened then. We would go to a designer who'd worked for many weeks on, let's say, 400 gates, if that many, optimizing the heck out of it. And then we would take it, and in a matter of a few hours, we'd give something back, and it was literally 30% smaller, smaller as in fewer gates, and 30% faster in terms of the critical pass through it. And for starters, they couldn't really immediately look at it because here's a net list, it's great. Well, you look at a net list, you can see nothing, so you have to draw the schematic yourself, which was really a step backward. And we figured that out pretty quickly. So we created also a schematics generator, which at that time I hadn't realized that's actually a place and route system. But out of that came something fantastic, because then we could go back, they would go away, and for a week we wouldn't hear anything, and they analyze because they couldn't believe it was right. They had worked so hard on it.
To go over that disbelief.
It's the disbelief. It's no way you can do that. I know how difficult this was. I worked for it on 3 weeks. And then they would come back and say, oh, this is unbelievable. This is great. And now you have the danger. Expectations are too high, right? But something better happened out of that, which is by being able to look together at the circuit, they would say, this is fantastic to get this so quickly. And then they say, but here, you could have done it differently, and it would be better. And it did two things. One, the people that really were able to say that, they were instantaneously experts with us, appreciating what we could do, and still they were their own people and being fantastic at it. And it made for an instantaneous alliance, because we would take those lessons, put them in, and at that time there were still a number of rules that you could apply, and then come back and say, well, here we fixed it. And people were, my stuff is now with Synopsys, right? I'm a little bit a synopsoid too now. And that made for a very long-term great evolution of improvements. And at that time, we, or shortly thereafter, we introduced this notion of measuring everything in terms of three vectors. Quality of results, QR, which is, at that time was speed, later became speed and power. Time to results, which is, of course, the weeks to days or hours, and cost of results, which at that time meant the area or the gate count, but it could also be some other factors of needing experts or something like that.
reducing a team of 50 down to 5 sort of thing?
Well, actually, if you look now, modern times, it would be more a team of maybe 20,
Yeah.
down to often a 1.
Oh.
Right? And so that parallelism existed, but at a degree of complexity that is literally 30 years later, right? And so full Moore's law 30 years later, and it's not like we do a whole chip, everything is ready and to go, but in very big blocks, it's amazing. And so now we have a similar set of questions of looking at very complex chips and say, well, what if you split them and have two simpler ones or two that then grow to the same complexity? For starters, it's really chip out. It's not like board design where you say, you have a board and now you bring the chips in from the outside. No, this is actually, the design has to be from the essence, which is chip out, because ideally you want the other chip to be just a continuation. And the only bothersome thing is that there's the connectors that are just dog slow compared to what's inside.
Bandwidth and power,
Bandwidth and power and speed. Yeah.
So when I speak to certain companies who are dealing with this, they're approaching it from, you have so many different abstraction layers when it comes to chip design that are essentially independently evolving of each other. And then in comes machine learning, and it's starting to re-blur some of those lines as you apply it. How are you dealing with that?
Well, there's two types of blurring, because there's verification blurring and there's creation blurring, let's say, right? And so verification blurring is old, meaning that you create a model of a transistor, and then the level of abstraction is suddenly, this ones and zeros thing. That's an unbelievable level of abstraction when you think about it. And then gradually we add some physics into it. And actually, one of the big distinguishing factors between the synthesis we brought to market is that most people didn't know. We had built-in timing.
Yep.
And timing is a physical characteristic. It's not a binary 0 1s. It's just that your 0 and 1s are not that good all the time, right?
Yep.
And so instead of click, click, it's like click, right? And so the fact that many verifications you can do by just zeros and ones, and if you know it's synchronous, you essentially have simplified the timing too into clock ticks. And so that's a classic example of maybe the single simplification that has been the best in the world ever. And I've always wondered, well, why do we really need a 0 and a 1? Why don't we just do ones? That's sort of boring because nothing changes, right? And so it's almost the minimum simplification that you arrive, and then very quickly this goes up. But the interesting is fundamentally the software coming down is also zeros and ones. And then they get further abstracted, of course, into languages or meta languages and so on. Except that if you now say, but we're going to have multiple chips coming together, that thing is a little heater there. What does it do to the speed of the other guy? Well, now the model needs to go deeper, grab some physics, and you can say, well, I have a physics. If the thing warms up, it runs half the speed or whatever it is. It's a little too simplistic.
Especially when it's stacked, right? Yeah.
Well, especially if it's stacked, right? And then you need cooling. Cooling is like essentially, but therefore systemic complexity.
So one of the common complaints of modern chip design, especially at the leading edge, is the cost of bringing these chips to market, design, manufacture, test, verification. And whenever I see the graphs produced by the analyst firms about what prices go into that, software is a slowly increasing part of that.
Slowly, as in like undervalue. Is that what you meant to say?
But it's to the point now where it's more than 50% of a chip design, sometimes, depending on who you talk to. Why is that? Well,
so what's your cost of going from your home to work? You're using a car. Isn't that a lot more expensive than some animal and some little cart?
It's a speed thing.
Well, it's a speed, it's convenience, it's so many things. I mean, what we do is amazing, but I'll get back connected
Sure,
to this. Is the complaint about it being more expensive to do things?
Well, I wouldn't say complaint. I'd say observation.
Yeah, you see, you made it sound a little bit more negative. It sounded so slightly bitchy, right? But the fact is, of course, I understand why. And yes, things are more expensive, but also so dramatically more complex.
Yep.
And I would argue any day that if it becomes too expensive, it will slow down. But I would argue it's become cheaper because suddenly you have these breakout of what you can do with the software above. And if the only thing you can do is listen to the radio in the 90s, well, damn, that was cool.
Yeah,
that was cool. And now there's no comparisons what you can do. And so what is interesting of the whole Sysmore era, that is sort of the, I would say, silicon up view.
Yeah.
And I want to paint it as an hourglass, right? Silicon up view, well, that silicon has just moved up because of much more complexity and capabilities. But because it's moved up, it's touched down on all the verticals where at the intersection the software now can impact whatever vertical you're in. And so when a vertical gets impacted, it touches an unbelievable large amount of economic space, right? And so if, just for argument's sake, you can make financial transactions 3% smarter than your neighbor, you're sort of raking it in.
Millions, yeah.
Right. But maybe another comparison is just, you take the industrial age, and the minute machines were able to move things, it opened up obviously a standard of living that had many downsides, we know that, but also changed the world. Well, this is not a standard of living maybe, but it's a standard of insight and understanding that is just remarkable. But what is so interesting is that the coming about of big data from all these verticals, all being different, and the intersection now with a new form of computation called AI or machine learning, with the ability to actually do it in reasonable time, right? So it's not like winning the chess game is going to take you 5 years of computation, and that's an old one, right? And nothing compared to today. No, it's actually very fast. Is that now you have the continued push of the Moore part of Moore's law, but you now have an economic pull. And when you have a push and a pull at the same time, that brings about amazing changes. And that is why I'm concluding that we have now a 20-year exponential of demand and needs and so on. And I always talk about techonomics, meaning that no difficult technology decision is made without also understanding the economics of it, because otherwise you can't afford it. And so when you say, well, is it not true that the design is much more expensive? That's a techonomic question.
Right.
And the question is, okay, how expensive is the technology versus how valuable is its outcome? And in some ways, it took the post-COVID combined with deglobalization push for people to appreciate that when you don't have a chip that's needed in a doorknob controller for a car that costs 53 cents, the 53 grand car cannot be sold. And for the first time, it's, these chips are valuable. How come we don't control them? But that is one of the reasons why the semiconductor industry is absolutely going to go to $1 trillion by this decade. So you pay what you get for it.
Sure. It's actually interesting that
you get what you pay for.
You get what you pay for. It's interesting you bring that up because I want to get your opinion on the fact that on the automotive industry especially, just to pick one vertical, we're seeing so many CEOs change to be former semi-CEOs, right? Because of this desire to have their own secure supply chain and bring everything out. What's your opinion on that? Does that just continue what you've just been saying?
Well, okay, so now you have the whole disruption of an industry that has been, all in all, unbelievably stable around one modus of locomotion that has been optimized and optimized and optimized first at the mechanical and fluid level and so on, and then at the electronic level to control essentially that. And then two things are happening, and I think they're completely independent. One is the notion of the electrification of the car, which is essentially getting off of fossil fuel and so on, and has some other advantages and disadvantages, but is fundamentally it requires an unbelievable change of the global infrastructure of energy. And then independently of that comes this notion of autonomous driving. And I remember, I do these exec forums with groups of 30, 40 top execs, and partially also fun evenings, and this must have been maybe 12, 13 years ago, when we saw in Silicon Valley they were not called Waymo then, but they were the little Google cars, and they essentially were driving around. And so suddenly it became, well, this is sort of obvious, this is going to happen. And I remember asking people in the room, so how many years will it take? And there were immediately two groups, like in 2 years everybody has one, and then the other was, well, not
20.
so. No, 2030.
Oh, right, okay.
And I tell you, so which one is it now? Well, it's difficult to answer because what we have already now is utterly defensive cars. So there's been enormous benefit of this. But, are you really going to take a nap at the steering wheel? Or is this one of those where when the steering wheel wobbles, it says, it's your turn now, right? Yeah. And so this level 3 where it can just pass the steering wheel back, to me, is completely unusable. But that also shows how level 4 and 5 are extremely difficult. So why do I tell you that? Because now most of the automotive companies are figuring out that the decision to go to level 4 or 5 implies re-architecting the very control of the vehicle with enormous smarts built in, and by the way, with very high degree of requirement to be actually better and provably better than human drivers. We know it could be better, or it is already better, but it's not very provable. And so the challenge there is for who is now driving the essence of the car, and the fact that they talk about software driven vehicles is a very big statement after, for decades, having, I think in German, they refer themselves as metal benders, right? Well, that's a far cry from that.
And now they're software developers.
They're now software benders, and you can't bend software too much. Right?
So, as I'm interviewing now, it's December 2023, and you've announced you're going to pass the reins over after 37 years to Sassine. How does it feel?
Well, for starters, there's a big piece that feels fantastic because Sassine is an unbelievably talented person that also has 25 years at Synopsys, has had big impact on many things that we've done, but has also grown up with starting with a background of being an application engineer. And nothing is better than to understand how painful it is for the customer than when you have to help them with your own software, right? And then from there, he moved into the sales function. And there, he actually was not just I'll just sell you stuff, but somebody who was capable of seeing the situation through the eyes of the customer and what the economic impact is and so on. And in that sense, gather a very high degree of trust that they of course always see us as part of the L and P&L. It's costly, but really it's what can we do to differentiate forward. And when you're on exponential, that's the driver. And then he became general manager, made many changes, pushed very hard for the AI capabilities, for example, but a number of others also, and very successful at that. And then spent some time at the corporate exec level as CEO and president. And so I have no doubt it's a person that in many ways, for many new things, will be better than I could ever be. And at the same time that I completely trust to also keep his mind on the values, the importance of people above everything else. Now, I've been preaching in our company, and I'm a preacher from time to time,
Sure,
surprise, that everyone should always, for themselves or for their team or we for the company, should look at version N+1, a very math-oriented version of saying develop, right? And it's so easy to preach to somebody else. And now I'm sitting here and say, well, okay, what is my N+1? And now I find out, it's when you just say you're going to do that, it's not so simple. And so my intent is to spend a month of disappearing completely. And part of that is just also after 40 years of literally non-stop sprints, just resettle a bit. But also to think through what's important. What is it that I can do for Synopsys, maybe also for the industry and for
because you're staying around as executive chairman.
Yes, I am. But, that's a thing that purposely is loosely defined. And I've been chair for a long time, so I know what to do for the board. And maybe I'll have a little bit more time. But I shouldn't...
Will you wander around the company and they won't let you into certain meetings anymore?
Well,
that's what will happen.
Well, and so those are all the type of things to learn. The most difficult thing to learn is, of course, I have God knows how many years of, hey, you want to grab things and move them. And that is learning. There's absolutely learning. I'm very conscious of it, but I'm now learning the emotional challenge of actually living up to that. But I know well that when you have high emotions, high and low, that means your mind is just working hard on it. And I'll master that at some point in time.
Sure.
But in that context, the first objective is support Sassine, because he has to find his own style. Well, he has his own style.
Well, I was going to ask you, what advice are you giving? You've known him for so long, but this is such a change. Is there any specific advice you've given him for this change?
I try to not do that.
Okay.
And I say I try because it's hard for me to not do it, right? And actually, this is the very thing I need to learn to resist, because he needs to, as much as possible, plot his own path to solidify it, also to be clear to all of our employees how he wants to run things and so on. Now, I don't think I can completely resist to not give advice, of course. But I need to learn to wait for him to ask me if he wants to. And so my intent is to move into a little bit other directions of stuff that he wouldn't have time or inclination, and that are yet important for us.
So looking big picture, sort of 5-10 years down the line, where do you want Synopsys to be? Where would you hope Synopsys would be under Sassine?
Well, we are in this very unique situation that we're in the middle of the ecosystem that brings the pyramid and whatever the opposite of the pyramid is. We're sitting in the middle of clearly enabling the computation above while harnessing the physics below. And the computation above is becoming way more demanding. And by the way, it's not just computation, it's also all the data and all that stuff. And the physics below is also becoming more demanding. And so difficult is our middle name, right? So that's been Synopsys for a long time. And so I think he will be perfectly capable of growing the company. He is very talented in managing the business side of things. And we have a team of technologists that absolutely will nail all these problems one after another. But it was all of those things, the ups and downs. You have to navigate through those. You have to keep hiring the best people. And best is not just most technology adept and so on. It's people that are fundamentally good people to work with. And so, continuing while evolving the culture is part of what needs to be done.
Well, I think our time is coming to a close. Thank you, Aart, for spending time with me. It's you've been such this big person in the industry for a long time. I'm glad I've caught you while you're still the CEO. And enjoy what sounds like really a partial retirement.
Yeah, the question is, retiring to what? Retiring is a weird word, right? And so the intent is just find the next phase that is, I'm still looking for impact, but I'm also looking for impact that has additional meaning, because there's so many things in the world that are changing at an enormous speed. And, increasingly companies are the new home for cultures and places where people align on the values. And I think we've built something that's good in that direction. We need to see what we can do to have an impact on the world that stays very positive.
That's a long way of saying he'll still be around.
Yeah. I hope so. Yes, I hope
awesome.
so.
Thank you very much,
Thanks,
sir.
Ian.
Thank you.
Pleasure talking to you. Really is.